Welcome everyone. It's June and we have another edition of Symmetry in Newcastle. Our speaker today will be Waldemar Hołubowski from the Silesian University of Technology in Gliwice, Poland. And he'll be talking about normal subgroups in the groups of column-finite infinite matrices. So thank you for coming, Waldemar, and the ground is yours.
I also thank you, and I am very grateful for the possibility to give a talk at such an eminent seminar. My talk will be on normal subgroups in the group of column-finite infinite matrices. This is a joint work with Martyna Maciaszczyk, which is a PhD student, and Sebastian Zurek, which finished a PhD 3 years ago. And here is a wrong date, May, it was June 7, 2021, Symmetry in Newcastle. And now we try to explain what are our plans. The classical result due to Jordan, Burnside, Dickson says that every normal subgroup of GL and K, general linear group of n by n matrices over a field K, with additional assumptions that n is greater or equal to 3, which is not contained in the center, contains special linear group of corresponding matrices. Alex Rosenberg gave description of normal subgroups of a more general linear group of a vector space of any infinite cardinality dimension over a division ring. Division ring means non-commutative fields, sometimes are called also skew fields. However, when he considers subgroup of the group of linear transformation G such that G minus identity has finite dimensional range, the proof is not complete. Such transformation, when we of the form G minus it identity operator, if such transformations has finite dimensional range, the image is of finite dimensional vector space, the proof is not complete. Such transformations are called finitary transformations. We fill this gap for countably dimensional vector space V and give description of the lattice of normal subgroup in the group of infinite column-finite matrices indexed by positive integers over any field. And now, what we can say more. This classical result says that every normal subgroup which is not contained in the center, which contains the group of, which coincides with the group of scalar matrices, must contain special linear group. Special linear group is in fact a commutative subgroup of general linear group. Moreover, the factor group, special linear group, factorized by intersection of special linear group with the center, is simple, and this is the very known tool to obtain a simple groups. Sometimes when we look at some other system, algebras, rings, also we factorize some objects by intersection with center, and usually these objects are simple. And the last group, this factor group, in case of finite field, define to us an infinite family of finite simple groups, projective special linear group of n by n matrix over finite field of Q elements. We note that such intersection can be non-trivial and depends on n and characteristic of K. For example, if K is a prime film, then such matrix is diagonal matrix X for non-zero X belongs to special linear group P minus 1 Fp, because we have such equality X to the power X P minus 1 is equal to 1. What we can say more, this restriction n is greater or equal to 3 is because of some exceptions, if n is equal to 2, we must exclude 2-element field and 3-element field. So the nice is if we give assumption n is greater or equal to 3, we have such a nice description. And in the work which was published in 1943 in a Bulletin of Société Mathématique de France, named Le déterminant sur un corps non commutatif, Dieudonné extended above result to the case general linear group of n by n matrices over any division rings. Of course, when n is greater or equal to 3. In fact, this paper is very, very important for algebras because it defines non-commutative determinant for general linear groups and studies the properties of its commutator subgroup. And the last section of this paper, number 14 on page 45, announced similar result for infinite dimensional case and contains only 3 sentences and no proofs. And what we can we look at endomorphism of a vector space V of any uncountable dimension over division ring and denote by general linear group of V is group of units. This is a group of all invertible linear transformations on V. Dieudonné considers the subgroup C of V of GLV in general case, which is generated by transvection. This means elementary transvection. So these are elements of general linear groups which has one on the main diagonal and one non-zero entry below or above the main diagonal, and they conjugate and say that this group C of V coincide with the commutator subgroup of F of G, the group of linear transformation G such that G minus identity has finite dimensional range, so over finitary transformations. Normal subgroups of F of G of finitary transformations, which are not contained in the center, contain the group C of V, and any proper normal subgroup of C is contained in the center. So we have the following result that the factor group C of V factorized by the intersection of C of V with the center is simple. The proofs of results announced by Dieudonné are left to the reader. We prove the following generalizations. The whole group CV is simple, not only the factor group, and moreover, if the division ring is a 2-element field, then the center is trivial and C of V coincides with this group of finitary transformations. Why Dieudonné do not remark the fact that the whole group CV is simple? Because he only rewrite results for finite dimensional group, the group of finite n by n matrices, and don't check this very, very easy remark. If it is very clear that the center of GLV contains all scalar transformations, which are some element of the center of multiplicative group of divisioning D times identity operator. Such elements are called homotheties, and every non-identity homotety G for such element, if we look at G minus identity, such element has infinite dimensional range. If a vector space is infinite dimensional and D is not a 2-element field. If D is a 2-element field, the center is trivial. So the intersection of C of V with the center is always trivial for infinite dimensional case, and the whole group CV is simple in these cases. This shows that we have some interesting remark which was not noted by Dieudonné. Now we look at more general case, we look at any finite cardinal, let Aleph delta be the cardinality of a vector space V. And we look at any cardinal which is less or equal to Aleph delta, and we denote by F nu, the set of all linear transformations with range of dimension less than Aleph nu. And there is a very new result. For example, one can read this result in Jacobson's book, Algebra, Volume 2, Chapter 9, which says, give characterizations of all proper two-sided ideals in the ring of endomorphisms of a vector space V over division ring. And such proper two-sided ideals which contain F sub 0 have a form F nu for some index nu greater or equal to 0 and less or equal to delta. So in fact, we have a chain of two-sided ideals in endomorphism ring and also in endomorphism algebra, the algebra. So we have a zero ideal, which contains only 0. F0, if we look, F0 is the set of all transformation with range which is less than Aleph 0, so have finite dimensional range. So these are finitary transformations. Next, we have all transformation which has range countable or finite dimensional. And here we have the maximal two-sided ideals, which contains all linear transformations which have the range of dimension less than dimension of this endomorphism ring or algebra. And it is clear that this situation, this description can be generalized to normal subgroups of general linear group of a vector space V. And it was done by Rosenberg in the paper, The Structure of the Infinite General Linear Group, Annals of Mathematics, 1958. And now we try to describe this result. Let Z star be the multiplicative group of the center Z of the division ring D, and for any cardinal which is less or equal to Aleph delta is cardinality of the dimension of space, vector space V. Rosenberg used such a notation. He denotes G nu 1, the subgroup of GLV, which consists of all elements of the form identity plus A, where A is some linear transformation with range less than Aleph nu. And clearly, these groups are normal subgroups of GLV. And if we look at G01, this is a group of finitary transformation. However, in contrast with the description of two-sided ideals in endomorphism algebra, the group of scalar operators also is a non-trivial normal subgroup in general linear group of vector space V. We see that if we have endomorphism ring of algebra and we look at two-sided ideal, if two-sided ideal contain identity, it coincides with whole endomorphism ring. So endomorphism rings or endomorphism algebra has no, for such a ring, scalars are not two-sided ideals. In the case of group, we have finitary transformations, we have, which is normal subgroup, we have scalars, and of course, if we take a direct product of the group G nu 1, which is which contains transformations with of the form identity plus something which has a range less than Aleph nu, and we multiply by the center, we also obtain a group which is normal in general linear group. And this is a substantial difference between the case of algebra of endomorphism, ring of endomorphism, and the general linear group. Now we stated the main result of Rosenberg paper, which is called theorem B. If n is a normal subgroup of general linear group of V, dimension of V is Aleph delta, n infinite dimension over division ring, then either first case I, such a normal subgroup is H times identity V, where H is a subgroup of multiplicative subgroup of the center of D. So this is a subgroup of scalar matrices, the subgroup of the center, times G nu of 1, where nu is greater than 0 and less or equal to delta. Or this is first case, or second case, this normal subgroup is contained in the smallest subgroup defined in this case, which we look at finitary transformations, direct product with the center. And this result describes completely the normal subgroup of GLB, which strictly contained this subgroup, the center times finitary transformations. This is a case I. And what says Rosenberg about case 2? He relates this result to Dieudonné papers and wrote, furthermore, in paper of Dieudonné, on the last page, Dieudonné studied the case, second case. He showed that either normal subgroup is contained in the center, or n contains G01 intersection with C, which is defined by Rosenberg as C sub 0. Moreover, C sub 0 is equal to the commutator subgroup of finitary transformations, and the group C0 factorized by C0 intersection with the center. This subgroup is simple, and G sub 0 divided by C0 factorized by C0 is isomorphic to the multiplicative group of D made abelian. What is bad in this citation of Rosenberg? We explain here in the following. Rosenberg defines C sub 0 as intersection of finitary transformation with C, where C is the group generated by element of class 2, element of the form identity plus A, where A squared is equal to 0. This element of class 2 are in fact generalizations of transvection in finite dimensional case. And says Rosenberg without proof that C0 is equal to commutator subgroup of finitary transformations. In Dieudonné notations, finitary transformations, notation of Dieudonné is F of V. This is notation of Rosenberg. And for notation of commutator subgroup, in Rosenberg paper and in Dieudonné paper, which is called C of V. And if we look at the theorem A of Rosenberg, his paper says that GLV is generated by element of class 2. It means that the subgroup generated by element of class 2 is in fact whole group, general linear group. And this intersection, finitary transformation with C, give the whole group of finitary transformation, and we cannot obtain its commutator subgroup. So unfortunately, the statement that C0 is defined in this way is equal to the commutator subgroup of finitary transformation. Earlier, in my earlier papers, I cited the paper by Rosenberg, but when I work with infinite matrices, and last time I worked with Lie algebra of infinite matrices indexed by positive integers, and when I proved some results for Lie algebra, I was interested in results for the group, general linear group of a vector space V. And I restrict to vector space V, which is countably dimensional, and restrict to a field K, because my results depend on some generation results for this group, and this group are proved for algebra of matrices, so I need commutativity of a division ring. So my assumption is that I look at the field K, and we fix a basis E sub 1, E sub 2 countable basis. Then this group of linear transformation corresponds to the group column-finite matrices indexed by positive integers over a fade key. So in each column, we have only finite number of non-zero entries in each matrix. And this is the group of inverted column-finite infinite matrices over K. And we need to define some subgroups, GLRF. This is a subgroup in column-finite matrices, group of column-finite matrices, which consist of all matrices which differ from identity matrix E only in first few rows. So in first few rows, we can have non-zero elements, and below these rows, we have only identity on the main diagonal, like in the identity matrix E. Of course, we need also that these are invertible matrices, so we need that in left upper corner, we have matrix which has non-zero determinant. And also, we look at the subgroup of this group of row finite matrices. We give additional assumptions that determinant of the submatrix in left upper corner is equal to 1. And also, we denote by DST scalar matrices. So alpha on the main diagonal, and alpha is not 0. And we used such symbol for the subgroup generated by H and H1, and such notation for internal direct product of two subgroups. And the first, our result is the following theorem. Sorry. First, I prove that some subgroups, scalar matrices, special linear groups of finite rows matrices, general linear group of finite row matrices, and direct product with scalar matrices of these two subgroups. These subgroups are normal in whole group of column-finite matrices. Moreover, this group SLFR and the factor group GLC column-finite matrices factorized by direct product of the center and group of with finite rows matrices. This is in fact what we called Euler finitary transformation in a countable case. This factor group is simple, and special linear group is also simple. And also we prove that group of scalar matrices and such factor groups are isomorphic to K square, to the multiplicative group of the field K. This can be summarized in the following picture. We have identity, the smallest subgroup of group of column-finite matrices in countable case. Here we have maximal normal subgroup, which is scalar matrices times a group of finitary transformations. The fact that this is maximal subgroup here follows from Rosenberg result. Here we have special linear group of finite row matrices with determinant 1, and Kloves and Hirsch in 1953 proved that this group is simple. Here we have scalar matrices, group of scalar matrices. This thick line means that the factor of this group by this is isomorphic to k square, to k star. Here, thin line means that this factor group by this group is simple. And we have such a rectangle. Here we noted that all these groups are normal in general linear group of column-finite matrices, but we have a question, what happened in this rectangle? This is a problem to solve. So first, the corollary, the group GLCF and K is perfect as it coincides with the commutator subgroup. The group of scalar matrices is the center of group of column-finite matrices, and SLFR is a commutator subgroup of GLFR. In fact, group of column-finite matrices coincide with all terms of its lower central series. And so, if we return to this picture, so we see that, in fact, to find all normal subgroups here, in fact, we need to find all subgroups of this direct product center times finitary matrices, finitary transformations invertible, which contains special linear group of finitary transformations. So we need to find all normal groups here. There is also very nice lemma in Rosenberg papers, which shows that all normal subgroups here are normal in the whole group of column-finite matrices and the group of GLV for any vector space V of infinite dimension. So we use, in fact, in description to reduction of our problem results of Rosenberg, results of Kloves Hirsch on simplicity of special linear group FR, and we also note that since, for example, scalar matrices is the center of GLCF, then every subgroup of scalar matrices is normal in the group of column-finite matrices. Because these scalar matrices are normal subgroup here. Moreover, if you have H1, which is normal in G, and G over H1 factor group is abelian, then all subgroup H of G such that such subgroup H contains H sub 1 is contained in G, such subgroups are always normal in G. So any subgroup of the group of finitary transformation containing SLFR is normal in GLFR. So we have, looking at this picture, we noted here that all subgroups here are normal in general linear group of column-finite matrices. All subgroups here which contains SLFR and are contained in group of finitary transformation, this group is normal here, so such group are also normal here in this direct product, and by Rosenberg result are normal in whole group. So we have here is we note that first from theorem B of Rosenberg, we have that all normal, proper normal subgroups of Walsey group of column-finite matrices are contained in the subgroup which is center times finitary transformation. And from this lemma in Rosenberg paper, all normal subgroup in this direct product are normal also in this group. this is some kind of transitivity of normality. This is not transitivity of normal subgroups in general by subgroups which are contained here. So also we note that this group is maximal normal subgroup of column-finite matrices, and the corresponding factor group is simple, which follows Rosenberg result. Simplicity of special linear group FR was proved by Kloves and Hirsch in this paper in Maciaszczyk in 1953. And moreover, this proof has some advantages because the proof is in fact shows that every normal subgroup of group of column-finite matrices, which is not contained in the center, contains a special linear group of finite row matrices. So we also used this fact in such manner in our proof. And now we are in fact able to describe the lattice of normal subgroups of column-finite matrices modulo the center. And we repeat this figure, which was earlier showed, with abbreviated notation. And thin line denotes that the factor group, thin line which connect H1 with H2, note that the factor group is simple corresponding, and if this line is thick, this factor group is isomorphic to K square. So we have the same lattice, sublattice of the lattice of normal subgroup in general linear group of column-finite matrices. And what we can say if we restrict to the K, which is a two-element field. We know that the Jordan Burnside Dickson result holds for all n matrices for n greater or equal to 3. But if we consider the field of 2 elements and 3 elements, we exclude 2 by 2 matrices. And now, if you look at this lattice, sublattice of normal subgroup with this rectangle, which is not solved yet, we see that if we look at the 2-element field, this group of scalar matrices is trivial because we have one non-zero element in the field of 2 elements. And also the group of finitary transformation coincide with the special linear group of finite row matrices. So this sublattice reduces to the group GL column-finite matrices, GL-FR group of finitary transformation, and identity of phi, identity operator on V. So we have such a remark, which was also omitted by Dieudonné, in fact. And now we know that it is clear that our result, theorem 2, reduces the problem of determining normal subgroup in the group of column-finite matrices, infinite matrices indexed by positive integers over any field K to the following problem: describe all normal subgroups of the group, the centers of scalar matrices, direct product with the group of finitary transformations, which contains a special linear group. This special linear group can be also written in the form identity matrix, which is contained in scalar matrices, direct product with the special linear group. And now we show the following result. All normal subgroups of this direct product of the center and the group of finitary transformations containing the special linear group FR which is a commutator subgroup of the group of unitary transformation, and all such normal subgroups which are direct product of groups have a form H1, direct product with H2, where H1 is a subgroup of scalar matrices of the center, and H2 is a subgroup of GLFR, which contain SLFR. This result is very simple, but even in this form, we find some normal subgroup which are not covered in Rosenberg papers. Rosenberg, in fact, omitted many normal subgroups given in this result. Say, for example, he did not consider subgroups H2, which are contained in general linear group of unitary transformations, which contain SLFR. He only looked at the group of unitary transformation times H sub 1, and of course, a group of special linear transformation FR. So, even in this case, we have many non-trivial normal subgroups which are omitted by Rosenberg's. But this is not the description of all normal subgroups. We start with the following example. We look at the natural homomorphism from the group of unitary transformation to the factor group of unitary transformation by its commutator subgroup of special linear group of finite rows. This group is isomorphic to the multiplicative group of the field K. By theorem 2, we also have that scalar matrices, the center is also isomorphic to K square. And we look at the following subgroup H of the direct product of the center and group of unitary transformation. We look at all pairs A and B such that f of B is equal to A. So, in fact, we move the considering of normal subgroups of this group, which contains a special linear group, to the problem of finding normal subgroup in two abelian groups which are isomorphic to K star. And one can easily check that this subgroup H is normal subgroup in the whole group of the center and unitary transformation, direct product. Moreover, if we look at intersection of H intersected with scalar matrices, such intersection is trivial, because if we have non-zero element here, then we have from the right hand, in the right hand of this pair, we have some element of coset A times SLFR. So the coset do not contain identity matrix, so we have this intersection is in fact trivial. Moreover, if we take intersection of H with the second factor, with the second member of direct product, this intersection covers all special linear group FR. Here we should have GL, intersection of H with GLFR is equal to SL. So we deduce from this fact that H is not a direct product in the group of column, is not a direct product. This is a very important fact. In fact, H is a subdirect product, which is called sometimes fiber product. So we find a new normal subgroup, H, which is contained in the center times the group of unitary transformation, which is not of the form, which is not a direct product of two subgroups. So in fact, we can explain what is the main idea in completing our problem. We use the fact that if H is a subgroup of abelian group G and phi is any isomorphism of H and a subgroup phi of G of H in G, then we can look at something which is called also the subgroup, which is diagonal subgroup. In this case, we consider all pairs G and the image of G under this isomorphism, where G runs over all elements of H. This subgroup is a subgroup of the direct product of two abelian groups G times G. If we look at identity isomorphism, so we have a pairs G, comma G. This group is in fact the known diagonal subgroup of this direct product. And now, by P sub I, we denote the natural projection on the ith component of a direct product. And the solution to our problem is now summarized in the following result. We have a theorem which completes the finding of normal subgroups which are contained here in the direct product of the center and the group of finitary transformations, which contains a special linear group of finitary transformation. If we have such a normal subgroup, then H is determined in a unique way by a quintuple, H sub 1, F sub 1, H sub 2, F sub 2, and phi, where phi is some isomorphism. H sub 1 is the intersection of first component of direct product with H intersection with the center. H sub 2 is intersection of H with the group of finitary transformation. And F sub I, we note this PI we understood here in something different way in earlier. This is projection of H onto the first component, and we see we also need some isomorphism of a factor group F sub 1 by H sub 1 to the factor group F sub 2 by H sub 2. And such quintuple four subgroups, H1 is contained in F sub 1, H2 is contained in F sub 2, and phi is isomorphism of these factor groups, define, in fact, in unique way, normal subgroup here, which contains SLFR. And isomorphism, the element xy belongs to the subgroup H if and only if we have the following equality. Phi of coset x times sub H sub 1 is equal to the coset y H sub 2. So this is some generalization of the previous remark example. And it is clear that if we take the quintuple H sub 1, H sub 1, so F sub 1 is equal to H sub 1, so here we have identity group, H sub 2, H sub 2, so here we have identity group. This quintuple corresponds to the direct product. In this case, H is a direct product of subgroups H sub 1, H sub 2. In general, H is only a subdirect product of P of 1 of H, so projection onto the first component of direct product times projection of H onto second component of the direct product. And in general, H is a fiber product, which is described, for example, by Gursa lemma. I found this Gursa lemma in unpublished note on group theory by Professor Nikolai Vavilov, and also there is some information on Wikipedia, but I don't check other books where this Gursa lemma is. And now something about the sketch of the proof. The problem to show that some subgroups in theorem 2 are normal, it is an easy calculation which use some facts about generation of the group of infinite matrices. And in this result, we use some result of Simon Thomas, some result of Paul Vermesch, some result of mine about infinite matrices, group of infinite matrices. And these results are not proof for groups over division rings, so we have not easy generalization to general linear groups over division rings. However, we know that by Waldemar result, all finite division ring is a field, so this is the problem only for infinite division ring. And now, if we return to the proof of theorem, the last theorem, which is a final step in the proof of description of all normal subgroups in the group of column-finite matrices, assumes that we have a normal subgroup in the direct product of the center L and the group of unitary transformations, which contains special linear group of unitary transformations. So P1 projection of H onto first component is normal in the center. This subgroup projection onto second component of this direct product is normal here, and H is a subdirect product of this direct product of these projections. We know that if this is a direct product, then we have H is a direct product, but sometimes H is not a direct product. And first remark is that the subgroups of projection of H onto the second component, which contains special linear group FR, are in one-to-one correspondence with subgroups of multiplicative group of the field by this canonical homomorphism. So our problem is equivalent to the problem of description of all subgroups H of abelian group A sub 1 times A sub 2, where A sub 1 is isomorphic to A sub 2, isomorphic to K squared. I used A sub 1, A sub 2 to have the better for notation, because it is easy then define H sub E as an intersection with search component of the direct product and second component and so on. So we know that this direct product is in fact a subgroup of H, and subgroup of H is contained in this direct product. We can factorize H sub 1 direct product with H sub 2 by this direct product H sub 1 times H sub 2. And we then reduce the finding of such subgroup H to the problem of finding subgroup A in this direct product of factors H sub 1 divided by factorized by H sub 1 times H sub 2 factorized by H sub 2. And such that this intersection Fi, which is F intersection with this first component or second component, such intersection as trivial. So we reduce to the case when H sub 1, H sub 2 are trivial. And we denote K sub I projection of A in this direct product on first component and on second component respectively. And now, from definition of Fi, it follows that for every x in K1, there exists a unique y in K2 such that xy belongs to F. Moreover, for every y in K2, there exists a unique x in K1 such that xy belongs to F. So this mapping x to y is an isomorphism of K1 with K2. So this, in fact, is this isomorphism which is in formulation of our main result. Now assume that we have some subgroups in first component and in second component, and isomorphism of factor groups Fi by H sub I. It then exists a unique subgroup H such that such intersection, and here we have projection, and xy belongs to H if and only if we have the following relation: phi of this coset is equal to this coset. And applying these remarks, in our case, we complete in fact the proof and we obtain this result. Subgroups of this direct product containing special linear group of unitary transformation are a one-to-one correspondent with such quintups, where here are subgroups H sub 1, H sub 2, F sub I, F sub 2, and phi is some isomorphism. So the answer to the question of how look likes this picture is not quite trivial, in fact, and we complete the description of the normal subgroups which are here, and by Rosenberg's normal subgroup in this group of the center direct product with unitary transformation are normal here. So using result of Kloff-Hirsch, using result Rosenberg, and some results on generation of column-finite matrices, in fact, we complete the description of the lattice of normal subgroups. And now, why I return to the group of column-finite matrices, because I earlier look at the algebra of column-finite matrices indexed by positive integer over the field K, and such matrices have only finite number of non-zero entries in each column. It forms an associative K algebra, and if we endow this algebra with a Lie product in the way that the Lie bracket is equal to AB minus BA, we obtain a Lie algebra of column-finite infinite matrices over K. By GLFR, we denote the Lie subalgebra of this algebra consists of all matrices which have non-zero entries in only finite number of rows. So we don't need to take minus identity operator. We look at all matrices which has non-zero entries in finite number of rows. And for such matrices, from this Lie subalgebra, we can define a trace. A trace is a sum of first n entries on the main diagonal if we have n non-zero entries in the matrix A. And this can be extended to the function on general linear group of finite row finitary Lie algebras to one-dimensional Lie algebra over a K field. And this algebra is commutative, and its kernel is called a special linear group of finitary transformation. These are the matrices which have a trace 0. By scalar matrices endowed with the Lie bracket, we denote the Lie subalgebra of all scalar matrices. So we also have alpha, which can be 0, and multiply by identity, infinite identity matrix. And with my previous PhD student, Sebastian Zurek, we obtain the lattice of ideals of general linear group of general linear algebra of column-finite matrices, and all ideals are in this picture. And we see that here we have the whole group. Here we have the direct product of the center of this Lie algebra with the Lie algebra subalgebra of finitary transformation. Here we have obvious subalgebra with trace 0. This algebra is simple. This algebra is one-dimensional over K. Here is the factor algebra is simple. Here is the algebra of finitary transformation, and we discover here many subspaces of this linear space, and all subspaces in fact are ideals here in the general linear group of column-finite matrices. So this description is much easier than in the answer in the case of general linear group. And looking at this answer, I also return to the group and obtain the answer to the group with Martyna, Maciaszczyk, and Sebastian Zurek. An anonymous referee rejected our paper which describes these lattices because we have not recent results, recent papers in our end. And what was very happy for us was that referee give us the paper of Penkov and Serganova. This paper in development and retrospective in Lie theory, in book of papers by Springer, has a note, remark, that in countable case, this Lie algebra has only 5 proper, non-trivial ideals. This is first, second, third, fourth, and fifth ideal. So they omitted this ideal as JK, and in fact, because these ideals are indexed by non-zero elements of the field, they omitted, in fact, an uncountable family of ideals because they consider infinite matrices over complex numbers. So we are happy that we can add this reference to our revised paper, and we show that this paper has a gap like Rosenberg, like Dieudonné, and so the moral is such that it is very nice to look at old papers because sometimes there are some gaps which we can fill up. I also will try to find other paper, the paper of Dieudonné. It is in this paper. This is a paper by Dieudonné, which defines non-commutative determinant, and the last page, in fact, this is the last page. Chapter 14, il est facile d'étendre le titre que nous avons fait du groupe GLNR au groupe GLE. So it is easy to extend our result for finite group of n by n matrices to a group of GL of a vector space V. And here we have the center, which is formed by homotheties, so scalar operators. We note that in infinite dimensional case, scalar operators have a matrix, in any basic have matrix alpha times identity matrix. And here we have a C of A, which is a commutator subgroup of F of E, which is the group of finitary transformation. And here we have also said that all normal subgroup of commutator subgroup, which are distinct from CA, are contained in the center. So if we factorize the group commutator subgroup SL of finitary transformation, in our case, by intersection with the center, we have a simple group. We show, in fact, Dieudonné rewrite this result as the result for n by n matrices without any looking at this result. So we have our theorem 1. And also we see that all proofs are so the reader can easily prove these results. A manuscript was recited by the redaction on July 9th in 1943. 3 days ago, there was a general in a radio in Algeria, which name was Charles de Gaulle, and she shouted to Français, "Vive la France libre, vive la République française." So this was very, very interesting time. And now I will look at Rosenberg papers, and I will show this part which contains theorem B. Here we have theorem B. We have this fact. So we have description of all subgroups normal which contains the center and times finitary transformation, and all other normal subgroups are contained in this direct product center times finitary transformation. And here is something, the proof of part I, first part, which is correct because we have proved many lemma earlier. And here there is a notation remark that G over G delta, where delta is maximal index of Aleph delta. This subgroup is simple. And next, he give remark about result of Dieudonné. And after this, he says that we say something more than Dieudonné, and this is the main also result which are used by us. Normal subgroups in this direct product center times finitary transformation are normal subgroups of G. This is some more general results, but we use in a countable case. All our results are in archive. You can also look at this result. There are also this is a paper of Klaus Hirsch, Dieudonné, Goursat, 1889. This is my monography about infinite matrices. This is a paper with Sebastian Zurek. This is a paper of Alex Rosenberg, paper by Thomas and Vermes about generation of group of column-finite matrices. So I am at the end. Thank you very much for listening to my talk.
Right. Thank you, Waldemar. Do we have any questions for our speaker?
Some people have questions, but I don't hear.
Well, yeah, there was a question in the chat somewhere like halfway or very much at the beginning of your talk. So I think that's when you were giving the introduction. And somebody asked whether it is important in the case of finite field that its characteristic does not divide the dimension. But that was
I
very
showed this
early.
example when the center intersection with the special linear group is non-trivial. And non-trivial because we have elements on the diagonal, which the product is equal to 1 in finite fields, finite simple fields. So this is chat. I have a problem with looking at the chat. Maybe you help me ask the question.
I have it open here.
Of course, I also explained that these classical results for finite matrices were proved by Jordan, Dickson, Burnside, Dickson for matrices of size greater or equal to 3. And in case of 2 by 2 matrices, we have 2 exceptions, 2-element field and 3-element field. In other cases, we have the same result, but for simplicity, in almost all books, this result is noted as n greater or equal to 3. And of course, when Dieudonné looked at infinite matrices, he forgot about the case of 2-element fields, which also give reduction of this lattice of normal subgroups. Finite division rings are finite fields. So extension of Dieudonné is in fact for infinite division rings. I have problem with extending my result for all division rings because I have no such results about the generation. I use my result about algebra of matrices, and in this case, I need commutative field as coefficient field at least.
Okay. Thank you, Waldemar, for the answer. Are there any further questions?
Yeah, I could ask a question, perhaps. George Willis here. Do you know of other papers that have cited the work of Rosenberg and Dieudonné and used their result with the gap?
I'm sorry for my English. I learned English only in elementary school. Would you repeat the question?
Yes. Are you aware of papers that have cited Rosenberg and cited Dieudonné and not noticed the gap in their claims?
First, I cited results of Rosenberg and Dieudonné using MAD reviews and other citations with no reading the papers exactly, but only a few times ago, I look at this paper and try to understand their proof. And I discovered that, in fact, Rosenberg omitted this example of normal subgroups which are contained in the group of direct product of center and finitary transformations, saying that all is done in Dieudonné papers. But the Dieudonné papers are restricted not to this direct product, but also to the group of finitary transformations, and find a commutator subgroup and nose. So in fact, the main problem was here. It is not true that all normal subgroups here, which contain special linear group of finitary transformation, are direct product of groups, one subgroup here and one subgroup here. And this was, in fact, the main observation that this is not true, and this was unfortunately was not contained in Rosenberg papers and in Dieudonné papers. Dieudonné look only on this group and this group, in fact, but omitted this rectangle.
Yes, I was asking whether you know of other papers since Rosenberg, say, who have cited this result without noticing the error.
Rosenberger move this result on normal subgroup from the result on two-sided ideals of algebra of endomorphism, or ring of endomorphism of a vector space of infinite dimensional. And after the Rosenberg papers, all people think that Rosenberg describe all normal subgroups.
Yeah.
I don't see any paper which describes this problem.
Okay, thank you.
I am sorry because Rosenberg notation, Dieudonné notation is very, very difficult for looking in the paper, and I use this notation in my case of countably dimensional vector space. We have the whole group of general linear group of a vector space, which consists of column-finite matrices. And here, this is the sublattice of normal subgroups. And here, this is the main area which we investigated, in fact, in last term of our talk.
Yeah.
How to find this subgroup normal here, which contains this group. By Rosenberg, these are also normal in the whole group. So I use results of Rosenberg, I use result of Klaus-Hirsch, and some result. This is result of Klaus-Hirsch is for matrices over a field. So I am sure that I can. This result also proves for infinite matrices in general linear group of every infinite dimensional vector space, but this is this needs very technical lemma. We must to find some results about the generation, prove it, and this is too much work to make it. And are you satisfied? Or?
Yes, thank you. Yeah.
Okay, do we have one last question for Waldemar? Oh yeah, there's one question in the chat from.
During the Second World War, many Polish people were in Great Britain, and they learned English. And one Poles at a lesson said that the following, because he learned, "Are you satisfied?" "Yes, I am satisfied." He wanted to take a bus, but the bus was full, and he explained his teacher that the bus was satisfied.
Yes.
So I am sorry for my English. And
Oh, so there's one last question in the chat. So
could you,
I will read what's in the chat. I have a question on groups on integers. Is there a possibility to compare the density of SLNZ in GLNZ? And also the speaker or the person asking adds that they're not a specialist in this subject, so perhaps something like in terms of a computation.
I do not think that this is a commutative ring integers. Moment. I also can look at the group if the basis is indexed by positive integer, I will have the same result. This is not difficult to prove. However, if we look at other is isomorphism of a group of general linear group of column-finite infinite matrices, we can look at the basis, which is, for example, indexed by rationals. And here we have some problem. I don't look at this problem. I use the fact that I choose a basis first, and next I look at the group of column-finite matrices. And the second question was about the density of subgroup of SL over a ring of integers in this group over integers. In the whole group of column-finite matrices over integers, I don't look at this situation. Maybe it will be not difficult to consider. I don't know now.
Okay. So I guess that concludes our seminar for today. So thank you very much for the talk, Waldemar. It was nice.
Yeah, thank you.
And we shall meet in 2 weeks' time again.
Thank you very much.
Thank you. Bye.